I've talked a lot about the coordinate vector of a vector in a vector space with respect to a basis. So maybe I really should prove to you that if we're given a basis, that there is exactly one way to write every element of the vector space in terms of that basis, and therefore that there's exactly one coordinate vector of a vector with respect to a basis. So I claim that if B is a basis of a vector space V, and little v is an element of that vector space V, then there is exactly one way to express little v as a linear combination of the elements of the basis B. Now the basis B spans the vector space V and is linearly independent. Now since it spans V, then there's at least one way to express any element of the vector space in terms of B. That's what it means to span. We can express anything in the space in terms of the elements of B. So since it spans, there is at least one way to express V as a linear combination of elements of B. So now I claim that so spanning gives us that. I claim that the linear independence of the basis prevents us from expressing a vector V two different ways in terms of the basis. So we claim that the linear independence of B prevents us from expressing V in two different ways. Let's say as two different linear combinations. So suppose that V can be written as a sum of AI VI as I goes from 1 to n, and as a sum of BI VI as I goes from 1 to n. So then A1 through AN and B1 through BN are two different and valid coordinate vectors of v with respect to the basis. But if that's true, then we can write 0, which is v minus v, as the difference between these two sums, because each one of these is v. And then the coordinate of v1 is going to be a1 minus b1. And the coordinate of v2 is going to be a2 minus b2, etc. The coordinate of vn is going to be an minus bn. But since this basis b is linearly independent, then we know that the only linear combination of its elements that's equal to 0 is the zero linear combination. So by linear independence, of b, the only linear combination equal to 0 is 0 v1 plus 0 v2, etc., up to 0 vn. So that means that a1 minus b1 is 0. And that means that a2 minus b2 is 0, etc. an minus bn equals 0. So all of those coefficients have to be 0, which means that all of the a's are equal to the corresponding b's. So this sequence of numbers a1 through an is actually equal to the sequence of numbers b1 through bn. That is, ai equals bi for all I. So these aren't two different coordinate vectors, it's the same coordinate vector twice. So that means that there is only one. We proved that there's at least one. If there's at least one and there's only one, then we could say that there's exactly one. So there's only one coordinate vector of an element of a vector space with respect to a basis B. Of course, if we change basis, we get a different coordinate vector with respect to the new basis. But if we're looking at one basis, then there's exactly one coordinate vector of the vector v with respect to that basis. The end.